Some discoveries unfold like a quiet whisper across the cosmos. Others, like the arrival of 3I/ATLAS, crash into the halls of science like a deafening alarm. For centuries, we believed our solar system was a relatively quiet corner of the galaxy, a peaceful haven drifting in a sea of predictable orbits and lifeless rocks. But the arrival of Oumuamua in 2017 shattered that illusion. Now, years later, the James Webb Space Telescope has identified something even more intriguing, an object far larger, far faster, and far more dynamic. It's called 3I/ATLAS. And according to early analysis from Webb's observations, it's on a path that defies typical cometary behavior, raising questions about its origins. It exhibits characteristics of comets, yet moves with a velocity suggesting an interstellar origin. It reflects light like ice, but emits chemical signatures, such as high levels of carbon dioxide, that are unusual for typical comets. In short, 3I/ATLAS is beginning to look like a unique interstellar visitor, distinct from known comets. And it's headed through our solar system with a trajectory that has left scientists eager to learn more. But is this truly the second interstellar visitor we've encountered? Or is it something new? Let's unravel the evidence and face a question astronomers are eager to answer. What is this object? What insights can it provide about distant star systems? When astronomers at the Vera C. Rubin Observatory first detected the faint, fast-moving blur of 3I/ATLAS against the backdrop of the stars, they assumed it was another long-period comet, an icy drifter, harmless, spiraling in from the distant Oort cloud. But within hours, that assumption fell apart. The object's trajectory was unlike anything they'd cataloged before. Instead of obeying the chaotic curves expected from gravity-bound rocks, this body followed a hyperbolic path that cut through the inner solar system, and its velocity, over 130,000 miles per hour, well above escape velocity, indicated that it had come from beyond the sun's gravitational influence. This immediately placed it into an elite category, only the third known interstellar object ever detected. But the real intrigue came when its orbit simulations revealed something notable. 3I/ATLAS would pass by several major planets at distances that allow for detailed observation: Earth, Mars, Jupiter, and then swing past the Sun, using its energy to slingshot out of the system. Each turn, each alignment seemed precise, not chaotic, like a traveler on a cosmic journey. Scientists ran the math again and again, and the odds of this being a typical cometary trajectory were low. But even more curious, its closest approach to Earth, at about 1.8 astronomical units, 270 million kilometers, would happen while our planet is partially shielded by the Sun, making it challenging for Earth-based observatories to observe, prompting reliance on space telescopes. After Oumuamua's unexplained acceleration and bizarre properties, NASA was determined to be ready for the next interstellar visitor. That's why, as soon as 3I/ATLAS entered the solar system, the James Webb Space Telescope was tasked with direct observation. It targeted the object using its near-infrared spectrograph, NIRSPEC, on August 6, 2025, hoping to identify its composition. What Webb found stunned the scientific team. The spectral signature of 3I/ATLAS initially resembled that of carbon-rich comets, dark, reflective, icy surfaces. But beneath those readings were anomalies that could not be ignored. First, it was unusually rich in carbon dioxide, CO2, with smaller amounts of water ice, water vapor, carbon monoxide, CO, and carbonyl sulfide, OCS. Second, its emission rates, including 129 plus or minus 1 kilograms per second of CO2, suggested active outgassing inconsistent with typical solar heating models for comets. And third, its coma, a cloud of gas and dust, showed a compact, symmetric structure, suggesting a large nucleus, possibly up to 46 kilometers in diameter. It wasn't definitive proof of an exotic origin, but it certainly wasn't typical of known comets either. James Webb's data was sent to a select team of analysts under NASA's Office of Planetary Defense. And for the first time since Oumuamua, internal discussions began to focus on its potential interstellar origins and what it could reveal about its parent star system. Whatever 3I/ATLAS was, it wasn't behaving like a standard comet. And the question became, what processes shape this object, and why now? To understand why 3I/ATLAS has NASA intrigued, we must return to 2017. Oumuamua, the first confirmed interstellar object, entered our system without warning. It tumbled, accelerated without clear outgassing, reflected light oddly, and vanished just as quickly. Renowned Harvard astrophysicist Avi Loeb proposed that Oumuamua might have been a fragment of alien technology, a light sail perhaps, or a probe designed to mimic natural objects. His theory was debated widely. But now, with 3I/ATLAS, some of those debates have resurfaced. Because this new visitor is not only larger than Oumuamua, potentially 7 times larger in diameter, it's also more active. Oumuamua passed close to Earth, allowing brief observation. 3I/ATLAS, on the other hand, follows a trajectory that makes it harder to observe from Earth, requiring space telescopes like Webb and Hubble. Its nucleus, estimated between 0.32 and 5.6 kilometers by Hubble, is surrounded by a diffuse coma, and it lacks a prominent tail, unlike typical comets. It moves at a staggering 210,000 kilometers per hour, suggesting it has been accelerated by gravitational interactions over billions of years. In every way, it's a unique object compared to Oumuamua. And now, some researchers suggest Oumuamua was a rare find, while 3I/ATLAS could provide deeper insights into interstellar chemistry. Behind closed doors, there's a hypothesis that scientists are exploring cautiously. They call it the interstellar chemistry hypothesis. It suggests that 3I/ATLAS is not a typical comet, but an interstellar object shaped by processes in a distant star system, possibly with a composition altered by long exposure to cosmic radiation. Its high CO2 content and compact coma are not the result of typical solar system formation, but of unique conditions in its parent system. Think of it like a cosmic fossil, carrying clues about a star system light years away. And perhaps it doesn't just drift. Perhaps its chemical emissions are a result of sublimation processes we don't fully understand. What if 3I/ATLAS is not just here to pass by, but to reveal the chemistry of another world? Like a cosmic puzzle, its data challenges our understanding of cometary formation. Just as scientists were beginning to piece together the strangeness of 3I/ATLAS, something occurred that heightened interest within key astrophysics institutions. The Deep Space Network, those massive antennas scattered across the globe that communicate with distant probes, detected a faint signal in the direction of 3I/ATLAS. It was narrowband, unmodulated, and pulsed at a frequency that resembled early Earth-based radar. What intrigued analysts was the regularity of the pulses. It wasn't a continuous emission, nor was it random. It had spacing, precision, structure. Within hours, the signal was escalated to multiple space agencies under standard protocols. Several observatories were directed to focus on 3I/ATLAS without public announcements. One internal NASA note stated, "The signal's origin is unclear and may be natural interference." Further analysis is needed. Although officials dismissed it as likely interference, the signal repeated 3 times and then ceased, prompting questions about its source. Could it be a natural phenomenon, or is it related to the comet's outgassing? While most telescopes rely on visible light, James Webb's real superpower lies in its ability to see in infrared, thermal radiation invisible to the human eye. This capability became critical as 3I/ATLAS began moving through a colder region of space just outside Mars's orbit. Infrared scans revealed something unexpected: a symmetric CO2-rich coma, declining in density with distance, suggesting a large active nucleus. Unlike typical comets, which emit irregular heat signatures due to their spinning, jagged nature, 3A/ATLAS displayed consistent chemical emissions. It was as if the object had a uniform structure, possibly indicating a more complex formation history. Even more intriguing was the discovery of a faint trail of particles behind the object, evenly spaced, suggesting sustained outgassing. These discoveries were not announced publicly, as they are still under analysis. Instead, agencies issued statements about ongoing comet observations. But the data shared among researchers suggests 3I/ATLAS is a comet with unusual properties, possibly shaped by its interstellar journey. With weeks of consistent trajectory tracking, researchers became confident that 3I/ATLAS would pass through a specific corridor between Earth and the Sun, likely making it difficult to observe from terrestrial telescopes during its perihelion around October 30th, 2025. But then, something curious was noted. The object showed slight deviations in its path, not fully explained by gravitational forces. These adjustments were small but measurable, suggesting possible non-gravitational acceleration, perhaps from outgassing. The new trajectory would bring it to about 1.8 astronomical units from Earth, close enough for detailed study by space-based instruments. This adjustment, scientists say, could be due to the sublimation of CO2 or other volatiles, a common feature in comets. But the precision of its path continues to intrigue researchers, prompting further observations to understand its dynamics. Sources inside major space agencies, including NASA, ESA, and the Japanese JAXA program, have shared that a symposium was held to discuss three I/ATLAS, focusing on its scientific potential. The topic: how to maximize observations of this interstellar visitor before it exits our solar system. According to reports, representatives discussed the importance of coordinating global telescopes to study its chemical makeup and trajectory. The conversation included plans for public engagement, ensuring transparency about findings to avoid misinformation. Some argued for open data sharing, saying the public deserves to know. Others emphasized the need for rigorous analysis before releasing preliminary results. What's notable is that this meeting took place before three I/ATLAS's closest approach, indicating the high priority of this object. And if a coordinated global effort is underway, it underscores the scientific value of this rare visitor. When Oumuamua passed through our solar system in 2017, it left behind a storm of questions, unanswered signals, and scientific curiosity. Its odd acceleration, its cigar-like shape, its minimal outgassing, all were anomalies. But three I/ATTLAS has not only recreated those mysteries, it has amplified them. New analysis shows that three I/ATLAS follows a hyperbolic trajectory distinct from Oumuamua's, but equally unbound by the sun's gravity. This has led scientists to classify it as an interstellar comet under the designation C/2025 N1 Atlas. What's even more intriguing is that its chemical profile, rich in CO2 and lacking a prominent tail, differs from Oumuamua's minimal emissions, suggesting a different formation environment. While Oumuamua left us guessing, 3I/ATLAS offers a wealth of data, providing a chance to study an interstellar object in detail. Days after Webb captured its first images on August 6, 2025, something unusual was reported. A section of its deep field observational grid experienced a data anomaly. NASA described it as a sensor calibration issue, but researchers noted that data from the region near 3I/ATLAS was temporarily unreadable. Adjacent sectors remained unaffected. Just before the anomaly, Webb detected a brief spike in infrared, possibly linked to the comet's outgassing. To analysts, this suggested a sudden release of material, perhaps CO2 or dust. Then the data stabilized, as if the event had ceased. This phenomenon raised questions among teams. Could the comet's activity interfere with observations, or was it a coincidence? Further analysis is ongoing to clarify this event. There is now a growing consensus within the astrophysical community that 3I/ATLAS will reach its closest approach to the Sun around October 30th, 2025, at about 1.4 astronomical units, just inside Mars's orbit. Unlike Oumuamua, which was already moving away by the time we discovered it, 3I/OA TLAS is still approaching, and it's showing signs of increasing activity. This has led to plans for further observations by Hubble in November 2025, using ultraviolet spectroscopy to study its gas emissions, and by Webb in December 2025, post-perihelion. Amateur astronomers have noted its brightness, around 12th magnitude, making it accessible to small telescopes with CCD cameras. Some report a diffuse coma, but no clear tail, consistent with professional observations. Either way, the clock is ticking. And with every hour that passes, 3I/ATLAS draws nearer to its closest solar approach. In scientific circles, a new hypothesis has begun to spread, cautiously but with increasing interest. What if 3I/ATLAS is not just a comet, but a relic of a distant star system, carrying a chemical signature that could reveal conditions billions of years ago? This theory gained traction when its CO2-rich coma was found to contain heavy carbon-13 isotopes, a rare feature that suggests a unique formation history. When our strongest infrared telescope looked closely, it detected these isotopes. When other telescopes observed, they confirmed the coma's reddish hue, possibly due to dust. Some researchers have started to refer to it as a cosmic time capsule because it carries clues about its origins. And now, as it approaches the sun, scientists must decide. Do we intensify observations? Do we develop new models to understand its chemistry? Or do we prepare for future interstellar visitors? As James Webb's sensors continued to analyze the object's surface, researchers began to notice something that challenged assumptions about 3I/ATTLAS's nature. The light it reflects is not entirely consistent with typical comets. There's a variation in brightness that, when analyzed, shows a pattern possibly linked to its rotation or surface composition. Spectral analysis suggests the presence of CO2, water, and other volatiles, but the ratios are unusual compared to solar system comets. NASA has shared preliminary findings in a preprint, noting that these patterns align with some early deep space observations, suggesting 3I/ATLAS may have been exposed to unique radiation environments. This data is still under review, but it indicates that 3I/ATLAS is responding to solar heating in ways that challenge existing models. Astrophysicists at the South Pole Neutrino Observatory explored the orbital path of 3I/ATLAS using cosmic particle data. They found no clear evidence of prior visits to our solar system, but the object's hyperbolic trajectory suggests it has traveled through interstellar space for billions of years. There are whispers among researchers drawing connections between 3I/ATLAS's path and theoretical models of interstellar objects. Could it be that such objects are more common than we thought? Suddenly, the idea of it being a one-off visitor seems less likely. Maybe it's part of a larger population of interstellar travelers. While the public narrative remains focused on scientific discovery, internal discussions reveal a proactive approach. NASA has activated observation protocols to coordinate global telescopes, ensuring maximum data collection. These measures involve open data sharing and public updates to maintain transparency. The most notable part? These protocols are about maximizing scientific return, preparing for future discoveries, and engaging the public responsibly. That means they are not just studying 3I/TLAS, but preparing for a new era of interstellar exploration. Just when the story seemed like it couldn't escalate further, James Webb detected something intriguing, a possible secondary feature in its data, perhaps a faint companion object or debris field trailing 3I/ATLAS. It's smaller, dimmer, and difficult to resolve, with no official confirmation yet. Scientists are analyzing whether this is part of 3I/ATLAS's coma or a separate phenomenon. This feature mirrors the comet's activity and occasionally varies in brightness, suggesting possible outgassing or fragmentation. Some now believe that 3I/ATLAS may be shedding material, offering a chance to study its composition further. And that means Earth is no longer just observing a single object, but potentially a dynamic system. As the object advances, astronomers have noted unusual activity in its vicinity. Space agencies across the globe, ESA, CNSA, and private observatories have reported consistent data on 3I/ATLAS's coma and trajectory. One report suggested a nearby asteroid showed minor orbital changes, possibly due to gravitational interactions with 3I/ATLAS, though not a space-time anomaly. James Webb recorded stable cosmic microwave background data while observing 3I/ATLAS, ruling out exotic phenomena. But its high CO2 output suggests it's actively evolving, possibly due to solar heating. You'd think that a signal from something as unusual as 3I/ATLAS would flood the SETI databases. But since the Webb observations, SETI has clarified that no confirmed signals have been linked to 3I/ATLAS. Public updates continue, and when questioned, SETI researchers emphasize that any signals detected are likely natural interference or require further analysis. A private radio array in Australia reported a faint pulse, but follow-up observations found no recurrence. This suggests the signal was not from 3I/ATLAS, but part of the noisy cosmic background. Scientists tracking 3I/ATLAS's trajectory were prepared for a typical hyperbolic curve. But what they observed was a slight deviation, possibly due to outgassing. The object is adjusting its path subtly, consistent with cometary activity. Recent models show its deceleration follows expected patterns for a comet, with no evidence of unnatural rhythms. Astrophysicists are studying whether this is due to CO2 sublimation or other processes. Because if it's the former, we're dealing with a comet that's more active than expected, offering a unique window into interstellar chemistry. With each new discovery, one thing becomes clearer. The implications of 3I/A-T-L-A-S extend far beyond astronomy. Scientists, educators, and communicators have joined the conversation. Space agencies are forming panels to assess not just scientific data, but public engagement strategies. If this object is confirmed to be a pristine interstellar comet, it could reshape our understanding of star systems, inform models of cometary formation, and inspire new missions. Some experts now argue that we are standing at a new frontier of discovery, where interstellar objects like 3I/ATLAS could become more common. The mere idea that we are observing a visitor from another star system could be the spark that redefines our place in the cosmos. Not in a century, not in a decade, but now. The James Webb Space Telescope, once hailed as our eye into the beginnings of the universe, has now become something more, a tool for studying our cosmic neighborhood. 3I/ATLAS is no longer just a mystery to be solved. It's a window into the chemistry and dynamics of distant worlds. It didn't stumble into our solar system. It's following a path shaped by eons of cosmic travel. It didn't simply appear. It arrived at a time when our technology could study it. And now, with every data point, every spectrum, every observation, it's clear this object is a scientific treasure. We are not alone in the sense that our solar system is part of a vast galactic community, crossed by objects like 3I/ATLAS. It may be a comet, a relic, or a clue, but above all, it is a chance to learn. And the most exciting part, it's not what it is, it's what we'll discover next. Because if 3I/ATLAS is just the third, then more are out there. So next time you look up at the stars, remember, not every glow is a star. Sometimes it's a comet carrying secrets from across the galaxy. And now we know it's here because we're ready to listen.